All right. So let's look at chapter 11. Okay, we're going to divide chapter 11's PowerPoint into two videos. So the first video, we're going to focus more on intermolecular forces themselves. And in the second video, we're going to look at the impact those intermolecular forces have on liquids. Okay, so excuse me, to start this off, we're going to look at states of matter. And obviously, we've talked about states of matter before in chemistry, but in this specific chapter, we want to look at states of matter as it pertains to the intermolecular forces of attraction between molecules. So, obviously, a solid, which is closely packed, tightly packed together, is going to have greater strength of intermolecular attractions than, say, a gas would, in which case the molecules are all spread out, right? Stronger forces are going to be responsible for bringing molecules together. Okay. Now, something that you may see in your textbook that I may mention, if you hear someone or that if you read in the textbook the condensed phase, we're talking about either a solid or a liquid. Okay. So just keep that in mind. It's something I want to point out as we start this off. Now, there is a really good table in chapter 11 that gives you some characteristics that go with each state of matter. Many of them are things you probably already know, all right, but keep in mind two little facts. Number one, all right, each of these has a marker about diffusion, okay? You can diffuse something through a solid, so just kind of keep that in mind. And at the bottom, it tells us that if we change the temperature, right, delta T, if the change in the temperature increases, then the atoms that are present in each of these things will start to vibrate a little bit faster, and you'll go from a solid to a liquid to a gas. Now, in order to overcome those, when the atoms start to vibrate, they get kinetic energy, right? They gain kinetic energy. And that kinetic energy can be used to overcome an intermolecular attraction. So when we're defining states of matter, what we're really doing is we're describing the balance between the kinetic energy of the particle, the temperature, right, and the attractive forces that are holding those particles together. So when you're giving an answer and it's in terms of intermolecular forces, use these three descriptors, okay? If you're talking about a gas, you need to point out that the kinetic energy is much larger than the forces of attraction. If you're talking about a liquid, hey, they're comparable, okay? And if you're talking about a solid, the energies of attraction much stronger than the energies of your kinetic, or your kinetic energies of your particles. Now, something to point out that we want to make sure we don't get mixed up. There is a difference between intramolecular and intermolecular, okay? When you see intramolecular, think a molecule. So that's how you form a molecule. That's a bond. An intermolecular force, on the other hand, is between. So inter-between. You could kind of think of it like that. It's the force of attraction between two molecules. Now, these intermolecular forces, we talked about them in year one chemistry. They are not as strong, okay, as our intramolecular bonds. But when you have millions and millions and millions of molecules in a mole, right, and they have all of these teeny tiny forces at play, the sum of many small forces is a large force, right? And so even though intermolecular forces are tiny on their own, as a group, they can impact things like the boiling points, the melting points. You can read the surface tension, this list I've got here. But it's the fact that there are so many molecules in that sample that you're looking at, that those little forces are all going to add together and impact those characteristics. So what are these intermolecular forces? Well, there are four that we want to know. The dispersion forces and the dipole-dipole forces we talked about last year, right? We talked about van der Waals. We also talked about hydrogen bonding, which, if you think way back, is a hydrogen on one molecule to an FO or N on another molecule. N, there we go. So we say that to kind of remember it, that hydrogen bonding is fun, okay? If you were in my class last year, you also talked about ion-dipole forces when we talked about water dissolving salts. So we've seen all four of these before. We know the first two are van der Waals. We know hydrogen bonding. But let's take just a little bit closer look. So a dispersion force is a temporary, randomly occurring dipole that appears in an otherwise nonpolar particle. So if I number these pictures here, this is like picture 1, picture 2, and picture 3, and these are points in time. So time is going this way. All right, so we have time progressing to the right. In the first picture, we see that these two atoms, it's helium in this case, the electrons are just moving randomly about their orbital. And in time period 2, in snapshot 2, we notice that this region of the molecule now has the electrons. So this is like a delta negative. This is a partial negative charge, which means the other side has a partial positive charge. And because of that, all right, the existence of that partial charge in atom B, the nucleus of atom A, which was right there in the middle, kind of moves a little bit to the right. It's attracted to that negative charge. There's an electrostatic attraction. Remember, that word means opposite charges attract. And the electrons are both moved, right, to the left a little bit. They are repelled out of the way. So when something randomly occurs like that, obviously it doesn't last very long, but that is a force of attraction that's going to hold those two atoms together. And when you're trying to, say, boil something, right, you're trying to overcome the forces of attraction so that the kinetic energy is much greater than the force of attraction. That's one more little force you have to overcome. Now, different molecules, different atoms have, different atoms will distort to different degrees, and we call that polarizability. So the more polarizable something is, the greater the chance of it distorting its electron cloud and these temporary dipoles to appear. If something has a really low polarizability, obviously the opposite is true, and it would not, or it would be very unlikely for it to form a temporary dipole. Now, there are some other factors that go into this to determining polarizability. Number one, we look at the number of electrons in the atom. The greater number of electrons present, the more dispersion force can be generated. The second thing we look at is the size of the atom. And usually we just identify that with the molecular weight. Larger molecular weight, more electrons present, right? More polarizability, or it's more capable of polarizing, okay? And the last thing we often look at is the shape. So if you have two molecules that have similar masses and you're like, hey, which one of these is more polarizable? Well, we're going to look for the one that has greater surface area. So something that's spherical, not a lot of points of contact between it and another molecule. But if something is linear, it has many points of contact between it and another molecule. So the greater the amount of surface area that's present, the greater number of those intermolecular forces, or dispersion forces in this case, can come into play. So those are the three things we look at. Now let's use polarizability and talk about boiling point. So polarizability increases with atomic size. That's what we just said on the previous slide. Larger molecules are going to then have higher boiling points than smaller molecules, okay? So why is that? Well, the greater the size, the more electrons are present. The more electrons are present, the greater the opportunity for dispersion to occur. The more dispersion that occurs, the greater the intermolecular force of attraction is that's holding two molecules together. And the greater that force, all right, the more force has to be overcome in order to affect a phase change. So when we look at this graph right here, and we see that, like, F2 has a much greater boiling point than neon. Well, why is that? Well, neon is going to be kind of spherical, right? Where F2 is going to be more linear, right? It's actually a linear molecule, okay? Look at the size, okay? Neon weighs 20 grams per mole. Fluorine is roughly 19 grams per mole, so 38 grams per mole. So it's almost twice the size. So the larger the molecule, the higher the boiling point likely is, okay? Another way to think about that is the easier something is to polarize, the lower the boiling point, all right? There we go. So let's look at the next intermolecular force, dipole-dipole interactions. So polar molecules have a positive and a negative end pretty much all the time. So we look at something like water, which I'm sure you've drawn about 1,000 times now in chemistry, and we know there are these two lone pairs at the top, and there is a permanent dipole present on water, right? We have a partial negative charge at the oxygen. We have partial positive charges on our hydrogens. We know that's there. If you put two dipole possessing molecules next to each other, their dipoles are going to interact with each other all of the time. So negative ends of molecule 1 are going to be attracted to positive ends of molecule 2. Now, it also means that there will be some repulsive forces present, right? If you get, you know, a negative end, like in water, the oxygen of one water near the oxygen of another water, that's going to push apart. So both of those things, the repulsion and the attraction, are present when you talk about dipole-dipole interactions. All right, well, what can we use that for? Well, let's go back to boiling point. If you have molecules that are roughly the same size, all right, the more polar the molecule, the higher its boiling point. And it's the exact same reason that we talked about with polarizability. The more polar the molecule, the greater the dipole-dipole forces that have to be overcome in order to affect a phase change, all right? So if we look at these four molecules here, we have propane, dimethyl ether, acetaldehyde, and acetonitrile. Well, acetonitrile is the most polar of the group, all right? You can see the polar rating right there in, I believe, Dalton's. And it's got the greatest polar character, or the most polar character, and so it has the highest boiling point. It's got the greatest strength of dipole-dipole force. Well, what if we have to compare the two? Well, like, what if we're looking at van der Waals and we want to know which is more important? Well, if the molecules are comparable in size and shape, then dipole-dipole interactions is the thing that you need to look at. If you're looking at molecules that have a great disparity in size, then you're going to look at dispersion forces, right? So water is actually a really tiny molecule. So let's say we wanted to look at like a water molecule, and we wanted to compare that to some kind of hydrocarbon. Well, a hydrocarbon is a long chain, right? What would we look at there? Well, this molecule is way bigger, so we would look at dispersion forces. That would probably be what we would compare. On the other hand, if you had, say, you know, I don't know, water and like HF, because that would be roughly the same size. Well, in that case, we're going to look at our dipole-dipole interactions. Hey, let's do that. So it's almost like I knew this graph was coming. So in this graph, we've got the molecular weight on the x-axis, and we're comparing it to the boiling point on the y-axis. And we're looking at periods 3, 4, and 5, okay? And we're looking at their bonding, all right, and how these molecules stack up to each other in their boiling points. So the general trend, if we just look from the right to the left, seems to be that the trend should go down. And with CH4, we actually see that that trend does. It does go down. But with NH3, HF, and H2O, we have these drastic departures from that trend. So what's going on in these period 2 elements? Well, it's pretty obvious, right? Hopefully you're picking up on the fact that hydrogen bonding is present here because we have H to an N, an F, or an O, right? FON, it's fun. So hydrogen bonding, a special kind of dipole-dipole force, is responsible for the increase in this boiling point. Well, we call this, all right, a hydrogen bond. The hydrogen bond only occurs when you have these really electronegative atoms on molecule 1, and you have hydrogen on molecule 2. So we look at F, O, or N. So kind of keep that together. Now, hydrogen bonds, all right, are going to if you want another way to kind of to think about it, you need to have a bare nucleus, all right? That can be a good thing, right? So what's the bare nucleus I'm talking about? I'm talking about the hydrogen. So these hydrogen bonds, that positive charge is a really strong positive charge. Okay, so that's something to keep in mind. And because it's nearly bare and it gives that really strong force of attraction to a negative charge, it allows for the boiling point to go through the roof, right? Because there is a greater force that has to be overcome in order to affect the phase change. Hopefully you're picking up on a trend with this little answer, right? Greater force to overcome to affect a phase change. Let's look at the last one. Let's look at ion-dipole interactions. So when we look at solutions that have ions dissolved into our solution, then and our solution is, say, polar, like maybe water, then it is the force or the strength of those force that make it possible for your ions to dissolve in polar solvents. So when we think about, salt, table salt, NaCl breaking down, it's the positive end of water that's going to be attracted to the chlorine ion, and the negative end of oxygen on the water that's going to be attracted to the positive sodium ion in salt in order to form these hydration shells. So the surrounding of the ion is called a hydration. We'll write that out. Shell. Okay, so that's the ion-dipole interaction. Now these are really strong. Okay, these are of all of the intermolecular forces we've talked about, these are the strongest. Okay, so let's look at a summary table. The weakest are on the left, our van der Waals forces. Our strongest are on the right, ion-dipole, and then actually ionic bonding. Okay, so ionic bonding falls under the intermolecular force of attraction because it's an electrostatic thing. Now, if you want to figure out which force is at play, follow the flow chart. So if you have some sample and there are no ions, well, if there's no ions, it can't be ion-dipole and it can't be ionic bonding, right? Neither of those two things are allowed. If you have ions, well, then it can't be any of these three, right? So that's a really good place to start. Let's go with no. So we've ruled out these two. The next thing you want to look at is, are there any polar molecules present? If you have no polar molecules, it has to be dispersion, all right? And then if you do have some polar molecules, you look for hydrogen bonding. So if you have H to NO or F, then we're going to be right there. So this is a pretty handy little flow chart. Now this is going to be the end of the first video, so take yourself a break. In the second video, we're going to look at the properties that are affected by intermolecular forces in liquids. So we're going to look at viscosity, surface tension, some things like that. In the meantime, if you have questions, send me an email. And if not, go ahead and jump into video 2.